Out there in the infinite blackness of space, something impossible drifts silently through the void, a planet still faithfully circling a star that died eons ago. This isn't science fiction. This is the ghost planet, a cosmic paradox that defies everything we thought we knew about how solar systems live and die. Picture this, a world locked in an endless dance with nothingness, orbiting the ghostly imprint of a sun that vanished without a trace. How does a planet outlive its own star? What strange forces keep it tethered to emptiness? And what does this celestial survivor tell us about the hidden rules of the universe? The discovery of this ghost planet isn't just a curiosity, it's a revolution. For centuries, we assumed planets couldn't exist without the warmth and light of a living star. But this lone world, clinging to the memory of its long-dead host, shatters that assumption. It's like finding a clock still ticking in the ruins of a forgotten city, its gears turning for no one. This planet shouldn't be here, and yet, against all odds, it is. That eerie resilience forces us to ask, what else have we gotten wrong about the cosmos? In this video, we're going on a journey to the edge of known science, where the laws of physics twist into something almost magical. We'll explore how astronomers stumbled upon this spectral world, how a star can vanish without taking its planets with it, and what happens to time, gravity, and even the fabric of reality in such an unthinkable place. From the violent deaths of stars to the secret lives of rogue worlds, this is a story about survival in the most hostile environment imaginable, deep space itself. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Finding this ghost planet was like solving a cosmic detective story where the clues were written in gravity itself. Astronomers first caught hints of its existence not by seeing it directly after all. A planet orbiting a dead star emits almost no light, but by observing the way it tugged on the fabric of space around it. The breakthrough came when they noticed something peculiar. Nearby stars weren't moving quite as expected. Their light wobbled ever so slightly, as if an invisible hand were gently nudging them. These tiny deviations, barely detectable even with our most advanced instruments, pointed to the presence of an unseen mass-warping spacetime. To piece together the puzzle, scientists turned to two powerful techniques. The first, called radial velocity, measures how a star's light shifts as an orbiting planet's gravity tugs it back and forth. But here's the twist: in this case, there was no star left to wobble. Instead, researchers had to analyze the ghost planet's influence on other stars in its neighborhood, like ripples from a stone thrown into a pond. The second method, gravitational microlensing, relies on a phenomenon where the planet's gravity bends and magnifies light from distant stars passing behind it, creating a fleeting but telltale brightening. It's like spotting a magnifying glass floating in space by the way it distorts the light behind it. What makes this discovery so groundbreaking is how it defies conventional wisdom. Planets we once thought couldn't outlast their stars. When a star dies in a violent supernova or collapses into a dense remnant, the explosion should obliterate or eject any orbiting worlds. Yet here we have a planet that somehow endured, a survivor of stellar apocalypse. Computer simulations now suggest that under rare conditions, a planet could be flung into a wider, more stable orbit during its star's death throes, escaping destruction. This ghost planet might have been hurled outward just as its star exhaled its final breath, leaving it circling an empty grave. The implications are staggering. If planets can persist in such extreme environments, our search for habitable worlds needs to expand beyond living stars. Could there be others like it, hidden in the ruins of dead solar systems? The discovery forces us to rethink not just where we look for planets, but what we consider possible in the life cycle of a solar system. It's a reminder that the universe is far stranger and more resilient than we ever imagined. The star that once anchored this ghost planet didn't fade quietly into the cosmic night. It met a spectacular demise. Picture a sun-like star, billions of years old, exhausting the last of its nuclear fuel. Its core collapses under its own weight, triggering a chain reaction that tears the star apart in a supernova explosion so powerful it outshines entire galaxies. Or perhaps it was a more modest star, shedding its outer layers in a shimmering planetary nebula before shrinking into a dense, Earth-sized ember known as a white dwarf. Either way, the star's death would have unleashed forces violent enough to vaporize nearby planets or fling them into the void. Yet against all odds, this ghost planet persisted. So how did it survive? The answer lies in a delicate cosmic balancing act. If the star collapsed into a white dwarf, the planet might have been far enough away to avoid being engulfed by the star's expanding outer layers during its death throes. Gravitational interactions could have nudged it into a wider orbit, placing it just beyond the reach of destruction. For a more massive star that became a neutron star or black hole, the planet's survival would depend on the explosion's asymmetry. A lopsided supernova might kick the star remnant away while leaving the planet relatively undisturbed. It's like a game of celestial pinball where the slightest miscalculation spells doom. But this planet somehow hit the perfect trajectory. But the ghost planet story doesn't end there. Even in death, the star's remnants still exert a gravitational pull. A white dwarf, though small, is incredibly dense, packing a sun's worth of mass into an object no larger than Earth. A neutron star, just a few miles across, spins rapidly, emitting beams of radiation like a cosmic lighthouse. And a black hole, its gravity is so intense that not even light can escape. Any of these remnants could still anchor the planet in orbit, a silent partner in their endless dance. The ghost planet might not orbit nothing, after all, just something invisible, a shadow of what once was. This raises another fascinating question. What does the planet experience in such a system? If it orbits a white dwarf, it's bathed in eerie, dim light from the fading stellar core. A neutron star might bombard it with deadly radiation, stripping away any atmosphere, and a black hole would warp time itself, stretching seconds into years for a distant observer. The planet's environment would be unlike anything in our solar system, a frozen, irradiated wasteland where the very fabric of reality bends under extreme gravity. Yet the most astonishing part isn't just that the planet survived, it's that we can learn from its existence. By studying this system, astronomers piece together the final moments of stars and the chaotic aftermath. It's like finding a fossilized footprint in the cosmic sand, a snapshot of a solar system's last gasp. Every detail, from the planet's orbit to the star's remnants, tells a story about how stars die, how planets endure, and how the universe constantly defies our expectations. This ghost planet isn't just a curiosity, it's a key to unlocking the secrets of stellar evolution itself. At first glance, the ghost planet's orbit seems impossible, a world circling nothing, like a dancer twirling around an absent partner. But the truth is even more fascinating. This planet isn't orbiting empty space. It's following the invisible fingerprint of gravity left behind by its dead star. Think of it like this. When you toss a ball into the air, it follows a predictable arc because Earth's gravity pulls it back down. Now imagine if Earth suddenly vanished mid-throw. The ball would keep moving in a straight line, right? Not quite. In reality, gravity's influence isn't instantaneous, it travels at the speed of light. So for a brief moment, the ball would still feel Earth's pull, as if the planet were still there. The ghost planet operates on a cosmic scale version of this principle. The star may be gone, but its gravitational waves linger, warping space-time like a heavy sleeper's impression on a mattress long after they've left the bed. Einstein's theory of general relativity explains this beautifully. Massive objects don't just create gravity, they bend the very fabric of the universe around them. Even when the star collapsed or exploded, its gravitational field didn't just switch off. Depending on how the star died, its remnant, whether a white dwarf, neutron star, or black hole, still exerts a pull. If the ghost planet orbits a black hole, for example, it's not dancing with nothingness but with one of the universe's most extreme gravitational anchors, a place where space and time twist into knots. But here's where things get even stranger. Without the star's constant energy output, the delicate balance of forces that kept the planet in a stable orbit is gone. Over time, the ghost planet's path could become unstable, like a spinning top slowly wobbling off course. Tiny gravitational nudges from passing stars or interstellar gas clouds, forces it could once ignore, might now push it toward drifting forever into the void. Some simulations suggest these worlds can cling to their orbits for billions of years before finally breaking free. Others show them spiraling inward, doomed to be shredded by tidal forces if they venture too close to their dead star's remnants. It's a high-stakes game of celestial pinball, where the slightest disturbance could mean the difference between eternal orbit and eternal exile. What's truly mind-bending is how this reshapes our understanding of planetary motion. We're used to thinking of orbits as fixed clockwork paths. Earth's yearly journey around the sun seems as reliable as sunrise, but the ghost planet reveals how fragile that stability really is. Its existence forces us to ask, how many other worlds are out there, silently circling the graves of their stars, waiting for gravity's silent music to fade? The answer could rewrite the story of how solar systems live, die, and sometimes, against all odds, endure. The ghost planet drifting through the void is far from the only world to outlast its star. Cosmic history is littered with survivors. Take PSRB 1257+12b, a planet nicknamed Draugr, after the undead creatures of Norse mythology. This world orbits a pulsar, the rapidly spinning corpse of a massive star that went supernova. Against all odds, Draugr endured the explosion that should have vaporized it, making it one of the first known pulsar planets discovered in the early 1990s. Then there's WD-1856+534b, a gas giant clinging to a white dwarf so closely that its year lasts just 34 hours. These worlds shouldn't exist, yet they do, each one a testament to the universe's capacity for defiance. What makes these survivors so remarkable isn't just their existence, but the clues they hold about planetary endurance. Pulsar planets like Draugr likely formed from the ashes of their star's destruction, coalescing from debris left behind after the supernova. White dwarf planets, on the other hand, might be the scorched remnants of worlds that once orbited a living star, stripped of their atmospheres but stubbornly holding on. Some could even be second-generation planets, born from the material ejected during their star's death throes. It's like finding a garden growing in the ruins of a volcano, proof that life, or in this case worlds, finds a way. Now let's bring this closer to home. Could Earth survive the Sun's death? In about 5 billion years, our star will swell into a red giant, engulfing Mercury and Venus. Earth's fate hangs in the balance. Some models suggest our planet might escape destruction by migrating outward as the Sun loses mass, but it would be a barren, lifeless husk. Even if it survives, the white dwarf Sun would provide little warmth, leaving Earth frozen in perpetual twilight. The ghost planets we've discovered serve as eerie previews of this possible future, showing us that planetary survival doesn't always mean habitability. Yet these cosmic survivors also offer hope. Their existence suggests that solar systems don't just vanish when their stars die, they transform. Planets can persist in the most hostile environments, adapting to conditions we once thought impossible. Some white dwarf systems even show signs of asteroid belts and debris disks, hinting at the potential for new planetary formation long after the star's demise. It's a reminder that the universe is full of second acts, and that even in death, solar systems can leave behind legacies. The more we study these resilient worlds, the more we realize how much we've underestimated planetary tenacity. They challenge our assumptions about where life could exist, perhaps not on a ghost planet itself, but maybe on moons orbiting one, warmed by tidal forces in the darkness. They force us to expand our search for habitable worlds beyond living stars, to consider the possibility of life in the coldest, loneliest corners of the cosmos. And most importantly, they teach us that the end of a star isn't always the end of the story. How does a planet end up orbiting a star that no longer exists? The answer isn't simple, it's a cosmic whodunit with multiple suspects. One leading theory suggests the ghost planet was there all along, a survivor of its star's violent death. Picture a gas giant like Jupiter, orbiting far enough from its host star to avoid being swallowed during the star's red giant phase or vaporized in a supernova. As the star collapsed, the sudden loss of mass could have flung the planet into a wider, more stable orbit, like a tetherball released when the pole suddenly shrinks. Observations of white dwarf systems support this idea. Some show signs of planetary debris, hinting that not all worlds were destroyed when their stars died. But there's another possibility. This planet might be an immigrant captured long after its original star perished. In the crowded stellar neighborhoods of our galaxy, close encounters between stars are common. A rogue planet, ejected from its birth system, could have been gravitationally snagged by the dead star's remnant. Computer simulations show that white dwarfs and neutron stars can sometimes steal planets from passing stars or even trap free-floating worlds. The ghost planet's slightly irregular orbit might be the smoking gun for this theory, a sign it didn't originate in its current system. The most intriguing hypothesis, though, is that the planet formed from the ashes of the dead star itself. When massive stars explode, they spew heavy elements into space, the very ingredients for new planets. Some astronomers propose that dust and gas from the supernova could have collapsed under gravity, forging a second-generation world. We've seen similar processes in pulsar systems, where disks of debris around dead stars give birth to new planets. If true, this ghost planet wouldn't be a survivor but a phoenix, rising from its star's funeral pyre. Each theory leaves distinct fingerprints. A surviving planet would likely be hydrogen-rich, like traditional gas giants. A captured world might have a composition mismatched to its dead star's chemistry. And a planet born from stellar debris would be unusually rich in heavy elements like iron and gold, telltale remnants of a supernova. Future telescopes could analyze the ghost planet's atmosphere for these clues, turning speculation into certainty. What makes this mystery so compelling is how it forces us to rethink planetary formation. We're used to neat narratives, worlds born in swirling protoplanetary disks, orbiting stable stars for billions of years. But the ghost planet shatters that simplicity, revealing a universe where planets can be survivors, wanderers, or even rebirths. It's a reminder that cosmic stories don't always end when the star dies. Sometimes that's when the most fascinating chapters begin. Detecting the ghost planet is like trying to spot a whisper in a hurricane without the light of a living star. Traditional methods fail. but astronomers have learned to listen to the universe in a different way, through the subtle distortions of gravity itself. When this unseen world passes between us and a distant star, its gravitational field acts like a lens, bending and magnifying the star's light in an event called microlensing. For a brief moment, the background star brightens in a telltale curve, revealing the hidden mass that caused it. It's as if the ghost planet leaves fingerprints on the fabric of space-time, and scientists have become experts at reading those cosmic smudges. Another clue comes from timing variations in the pulses of nearby neutron stars. These ultra-dense stellar corpses spin with metronome-like precision, beaming radiation across space like lighthouse beams. But when an invisible planet tugs on them, their rhythm stutters a delay of mere microseconds that betrays the presence of an unseen companion. It's like hearing a clock tick slightly off beat and realizing something invisible is gently nudging it. These methods don't rely on light at all. They map the universe through its gravitational shadows, turning the ghost planet's greatest camouflage, its darkness, into the very thing that gives it away. Yet the challenges are immense. Microlensing events are fleeting, sometimes lasting just hours, and they never repeat. Astronomers must monitor millions of stars continuously, hoping to catch that one critical moment when alignment and gravity conspire to reveal a hidden world. Even then, the data is often ambiguous. Was that blip a planet, a passing star, or just noise in the detectors? Distinguishing a ghost planet from other cosmic oddities requires painstaking analysis, combining observations from multiple telescopes across the globe. And if the planet orbits particularly far from its dead star, its gravitational signal becomes vanishingly faint, like trying to hear a single raindrop in a thunderstorm. The future, however, holds promise. Upcoming missions like the Nancy Grace Roman Space Telescope will scan the Milky Way's bulge, where stars are densely packed and microlensing events are more common. Its infrared eyes could spot planets orbiting white dwarfs or black holes by their subtle thermal signatures, faint heat left over from their formation, or tidal heating from gravitational stresses. Meanwhile, next-generation gravitational wave detectors might sense the ripples produced by a ghost planet's motion around a neutron star or black hole, adding a whole new dimension to the hunt. What's truly exciting is how these techniques could unveil an entire hidden population of ghost planets. If current discoveries are any indication, there may be countless more worlds lurking in the graves of dead stars, each with stories to tell about survival, cosmic chaos, and the resilience of planetary systems. Every new detection pushes the boundaries of what we thought possible, proving that even in the darkest corners of space, gravity never stops telling its secrets. Dark matter, the universe's most elusive ingredient, might hold the key to the ghost planet's impossible orbit. We can't see it, can't touch it, yet its gravitational fingerprints are everywhere, shaping galaxies and bending light across the cosmos. Now, some scientists wonder, could this invisible force be the hidden hand keeping the ghost planet tethered to its vanished star? Here's why this idea isn't as far-fetched as it sounds. Dark matter outweighs regular matter 5-to-1, meaning its gravitational influence dominates vast regions of space. If the ghost planet drifts through a dense clump of dark matter, what physicists call a halo, the combined pull of those unseen particles could mimic the gravitational anchor of a dead star. Picture a spiderweb you can't see, its delicate strands of dark gravity gently tugging the planet into a stable path. Computer models suggest certain dark matter configurations might even create temporary orbital stability, acting like an invisible substitute for the missing star's pull. But there's a catch. Dark matter halos are typically spread across enormous distances, far more diffuse than a collapsed star's remnant. For this theory to hold, the ghost planet would need to orbit within an unusually concentrated pocket of dark matter, something akin to a cosmic pothole in spacetime. Some speculative theories propose the existence of dark matter disks or even exotic structures like dark stars, which could provide the precise gravitational profile needed. Others argue the planet might be trailing through a dark matter stream, a ribbon of dense particles left behind by a smaller galaxy torn apart long ago. The implications are staggering. If dark matter does influence the ghost planet's orbit, it would be the first direct evidence linking this enigmatic substance to individual planetary systems. Normally, we only detect dark matter's effects on galactic scales, its ability to warp entire clusters of stars. Finding it sculpting the path of a single planet would revolutionize our understanding of how dark matter interacts with ordinary matter. It might even hint at entirely new physics, where dark matter isn't just a passive backdrop but an active player in the life cycles of worlds. Of course, this remains highly speculative. Critics point out that known dark matter distributions can't easily explain the ghost planet's precise orbit without invoking untested phenomena. Alternative explanations, like an undetected black hole companion or complex interactions with other rogue planets, might fit the data better. Yet the very possibility ignites the imagination. Could there be entire populations of dark matter planets, worlds orbiting nothing but the gravity of the unseen? Might dark matter's influence explain other cosmic anomalies, from strangely clustered star movements to galaxies that rotate too fast? The ghost planet may have started as a curiosity, but it's become a cosmic laboratory, one where the deepest mysteries of gravity, stellar death, and now dark matter collide. Whether or not dark matter proves to be the missing piece of this puzzle, the investigation itself pushes astrophysics into uncharted territory. After all, the universe has never been shy about appending our assumptions. Why should this ghost be any different? Imagine two lost souls wandering the cosmos, one untethered, drifting endlessly between the stars, the other forever circling an empty throne. Rogue planets and ghost planets might both lack a living sun, but their stories couldn't be more different. The rogue planet is a cosmic castaway, hurled from its birthplace by gravitational chaos, doomed to wander the interstellar void alone. The ghost planet, though, it's a loyalist clinging to the memory of its dead star, bound by gravity's invisible threads to a corpse. The key difference lies in how they became orphans. Rogue planets often meet their fate early, ejected from unstable young systems when gravitational tugs from sibling planets or passing stars send them careening into the abyss. Picture a game of planetary pinball where one world gets flung out of the game entirely. Some might even form alone in interstellar space, collapsing directly from rogue gas clouds too small to ignite into stars. These nomads don't orbit anything, they're true free agents, drifting wherever the galaxy's tides take them. Ghost planets, on the other hand, are relics of a system's death throes. Their star didn't abandon them, it vanished, leaving behind a gravitational echo. Unlike rogues, these worlds maintain their orbits, tracing ellipses around white dwarfs, neutron stars, or black holes. That's why they're so rare. Surviving a star's violent end requires a perfect cosmic balancing act. The planet must be far enough to avoid destruction during the star's death, yet close enough to remain gravitationally shackled to the remnant. It's the difference between a leaf blown from a tree and one still dangling from a withered branch. Their behaviors diverge dramatically too. A rogue planet, unchained from any star, experiences perpetual midnight, its surface freezing to temperatures near absolute zero, unless internal heat or tidal forces from moons provide warmth. Some could even harbor subsurface oceans, kept liquid by pressure and radioactive decay. A ghost planet, meanwhile, might still feel tidal heating from its dead star's remnant, or bask in the faint glow of a cooling white dwarf. Orbit a pulsar and you're bombarded with deadly radiation. Orbit a black hole and time itself stretches and warps. Detection is another challenge. Rogue planets occasionally reveal themselves through microlensing events, their gravity briefly magnifying distant stars as they pass, a telltale flicker in the darkness. Ghost planets are even trickier. Without a star's light to illuminate them, we rely on subtle gravitational wobbles in the dead remnant's motion or distortions in surrounding debris disks. It's like trying to spot a moth against a black wall by watching how it disturbs the air. Why does this distinction matter? Because these worlds represent opposite extremes of cosmic survival. Rogues show us the chaos of planetary youth, where gravitational bullies eject the weak. Ghost planets teach us about endurance, about systems that refuse to let go even in death. Together, they paint a fuller picture of how planets live, die, and sometimes against all odds, persist in the universe's most unforgiving corners. Finding more ghost planets isn't just about adding to a cosmic catalog, it's about rewriting the story of how solar systems die. Right now, astronomers are combing the galaxy for these elusive worlds, armed with tools that listen to gravity's whispers rather than relying on starlight. The first discovery shattered expectations, proving planets could outlive their stars. Now the burning question is, was that a fluke, or are ghost planets lurking everywhere we've failed to look? The hunt begins with microlensing surveys, where telescopes like the optical gravitational lensing experiment scan millions of stars for the telltale flicker of an unseen planet's gravity bending distant light. But spotting these events is like catching fireflies in a hurricane, rare, fleeting, and easy to miss. That's why new missions like the Nancy Grace Roman Space Telescope are game changers. Launching in the next few years, Roman will monitor the Milky Way's crowded core, where the dense stellar soup makes microlensing events more frequent. Its infrared vision can pierce through cosmic dust, potentially revealing ghost planets orbiting white dwarfs or black holes by their faint heat signatures. Another frontier is pulsar timing. Neutron stars spin with atomic clock precision, and even a tiny planet's tug creates detectable hiccups in their rhythmic pulses. The Square Kilometer Array, a next-generation radio telescope, will listen for these minuscule delays across thousands of pulsars, effectively turning dead stars into planetary detectors. It's like using a network of celestial metronomes to sense invisible dancers in the dark. What makes the search so urgent is the potential to uncover an entire hidden population. If ghost planets are common, it suggests that stellar death doesn't always mean planetary annihilation. Some worlds endure, rewriting the rules of solar system evolution. Imagine entire graveyards of dead stars, each with its own entourage of surviving planets. Some could even be frozen time capsules, preserving atmospheres and geology unchanged for billions of years since their star's demise. The implications stretch beyond astronomy. If life exists in the universe's coldest corners, ghost planets orbiting white dwarfs might offer unexpected refuges. Tidal heating or residual warmth from radioactive elements could maintain subsurface oceans under ice shields, much like Jupiter's moon Europa. While these worlds would never bask in sunlight, they might harbor chemistry complex enough to sustain extremophile life, a haunting possibility that expands the horizons of astrobiology. Upcoming missions promise even bolder revelations. The European Space Agency's Gaia spacecraft, already mapping 1 billion stars, could pinpoint subtle wobbles in white dwarfs betraying unseen planets. Meanwhile, the Vera C. Rubin Observatory's decade-long survey might catch ghost planets transiting their dead stars, silhouetted against the dim glow of stellar remnants. Each new detection chips away at the mystery, showing us that the universe's afterlife is far richer and far stranger than we ever dreamed. The search for ghost planets is more than a scientific endeavor. It's a cosmic archaeology dig. Every discovery peels back layers of galactic history, revealing how solar systems transform when their stars burn out. And with every new ghost found, we're forced to ask, in the grand cemetery of the cosmos, how many other silent survivors are waiting to tell their stories? If you could stand on the surface of the ghost planet, you might witness time itself stretching and twisting like taffy. Einstein's theory of relativity tells us that gravity doesn't just pull on objects, it warps the very fabric of spacetime. Near the remnants of a dead star, whether it's a white dwarf, neutron star, or black hole, this effect becomes extreme. The closer you get to these ultra-dense remnants, the slower time ticks compared to the rest of the universe. For the ghost planet, this means a single orbit. What we'd call a year might pass in what feels like days for us, while centuries slip by elsewhere. It's like living next to a cosmic slow-motion button, where the rules of time as we know them no longer apply. Take the famous example of a black hole's event horizon. To an outside observer, time appears to freeze for anything approaching that boundary, even as the falling object experiences time normally. The ghost planet isn't likely that close to its dead star's remnant, but even at a safer distance, the effect would be measurable. If the planet orbits a neutron star, its intense gravity could slow time by a fraction of a second per year relative to Earth. That might sound negligible, but over millions of years, those fractions add up. Imagine an astronaut on the ghost planet aging just slightly slower than their twin back on Earth, a real-life twist on the twin paradox thought experiment. But here's where it gets even stranger. If the ghost planet star collapsed into a black hole, the time dilation could become dramatic. At a certain distance from the black hole's edge, known as the photon sphere, light orbits in a perfect circle. A planet here would experience time so warped that a single hour could equal years for distant observers. While it's unlikely the ghost planet sits this close, such orbits are notoriously unstable. Even a more distant path would still bend time in eerie ways. Seasons, if they exist at all, might stretch across millennia. A sunrise, if there were one, could take lifetimes to crest the horizon. This time warping isn't just theoretical. We've already observed it in action. Atomic clocks on GPS satellites, which orbit Earth at high altitudes where gravity is weaker, tick slightly faster than those on the ground. The difference is tiny, about 38 microseconds per day, but crucial for accurate navigation. Now scale that up to the gravitational extremes of a dead star, and the effects become far more pronounced. The ghost planet's very existence forces us to confront a universe where time isn't a constant river but a malleable stream, bending around massive objects like water around a stone. What does this mean for the planet's potential inhabitants? Hypothetically, any life that evolved there would experience time differently than we do. Biological processes, from cell division to evolution itself, might unfold at altered rates. A civilization rising on the ghost planet could watch galaxies evolve in what feels like generations, while their own history stretches lazily across cosmic epochs. Of course, the planet's harsh environment makes life improbable, but the fact that time itself behaves so differently there reminds us how provincial our Earth-bound perception of reality truly is. The ghost planet's defiance of time isn't just a curiosity, it's a living laboratory for relativity. By studying its orbit, astronomers can test Einstein's predictions under conditions impossible to replicate on Earth. Every wobble, every microlensing event is a clue to how gravity and time intertwine in the universe's most extreme environments. And as we uncover more of these time-warped worlds, we're not just mapping planets, we're charting the very boundaries of physics itself. A planet without a star faces an almost impossible challenge holding onto an atmosphere in the freezing darkness of interstellar space. Yet the ghost planet might defy this expectation through sheer cosmic ingenuity. One possibility is that its atmosphere has frozen solid, collapsing into icy layers on the surface like a global glacier. We've seen this with Pluto, where nitrogen and methane frosts cling to the ground in temperatures nearing absolute zero. But unlike Pluto, the ghost planet has no occasional sunlight to sublimate these ices back into gas. Its air could be locked away permanently, a frozen relic of its warmer past. Another scenario involves tidal heating, the gravitational flexing of the planet's interior by its dead star's remnant. If the ghost planet orbits a neutron star or white dwarf in an elliptical path, the uneven pull could generate enough internal heat to maintain subsurface liquid oceans, much like Jupiter's moon Europa. These hidden seas might release gases through cracks in the ice shell, creating a tenuous, localized atmosphere. Imagine geysers erupting in slow motion, spewing water vapor or even methane into the void, only for it to snow back down in the endless cold. Then there's the wild card, radioactivity. Planets with uranium and thorium-rich cores could generate heat for billions of years, potentially powering volcanic activity that replenishes atmospheric gases. Mars, though not a ghost planet, shows how this works. Its thin atmosphere still bears traces of volcanic outgassing from ancient eruptions. If the ghost planet's core remains active, it might cough up just enough gas to maintain a whisper-thin shroud, even without a star's energy. But the real question isn't just whether the ghost planet has an atmosphere, it's whether that atmosphere could ever cradle life. In the absence of sunlight, organisms would need another energy source. Hydrothermal vents, like those on Earth's ocean floors, could provide heat and chemicals for extremophile microbes. Tidal forces might churn nutrients through subsurface oceans, creating oases in the dark. We've found life thriving in Earth's most hostile environments, from Antarctic ice to acidic hot springs. Could the ghost planet's hidden depths harbor similar tenacious survivors? The answer hinges on time. Atmospheres around dead stars slowly erode, stripped away by stellar winds or cosmic radiation. A planet might hold onto its gases for millions of years, even billions, but eternity is a long time to resist the void. Yet if any world could cheat death, it's this one. The ghost planet has already beaten impossible odds by surviving its star's demise. Who's to say it hasn't found a way to keep breathing in the dark? Even the most resilient cosmic survivors face an expiration date, and the ghost planet is no exception. Right now, it drifts through the void, locked in a gravitational embrace with its dead star's remnants. But the universe is anything but static. Over billions of years, subtle forces will conspire to disrupt this delicate balance. One possibility is ejection. A gravitational nudge from a passing star or interstellar gas cloud could fling the planet into the abyss, severing its last tie to the system it once called home. Picture a spinning top wobbling off its axis, except this top weighs trillions of tons and its fall could last millennia. Collision is another grim prospect. The ghost planet's orbit, already unstable without a living star's steadying influence, might decay over time, drawing it inward toward its dead host. If that remnant is a white dwarf or neutron star, tidal forces could rip the planet apart long before impact, scattering its remains into a glowing debris disk. Or imagine a darker fate, a slow-motion plunge into a black hole where the planet would stretch into a stream of atoms spaghettified before vanishing beyond the event horizon, its story erased from the universe. Yet there's a third, quieter destiny, cosmic erosion. Without a star's warmth or solar wind, the ghost planet's surface would be bombarded by interstellar radiation, micrometeorites, and cosmic rays, slowly sandblasting away any remaining atmosphere or surface features. Over trillions of years, even its rocky core might crumble into dust, leaving behind nothing but a faint gravitational whisper, a ghost of a ghost. Timing is everything. If the planet orbits a white dwarf, it could persist for hundreds of billions of years, outliving most stars in the galaxy. But if its path crosses a dense region like the Milky Way's core, gravitational chaos might cut its lifespan short. The same forces that sculpt galaxies' tidal streams, dark matter halos, even the galaxy's inevitable collision with Andromeda, could rewrite the planet's future in an instant. What's haunting is how ordinary its fate might be. Countless worlds likely share this trajectory, each one a testament to the universe's impermanence. The ghost planet story isn't just about one world's endurance, it's a preview of what awaits all solar systems, ours included. Long after the sun dies and Earth freezes, our planet too might circle a cooling stellar corpse, waiting for gravity's final verdict. The cosmos doesn't do forever, but for now, this ghost keeps dancing. Science fiction has always been a mirror for our cosmic curiosity, and ghost planets have starred in some of the genre's most haunting tales. Take Doctor Who's Midnight, a world bathed in lethal radiation where an unseen entity hijacks language itself, a chilling metaphor for the unknowable dangers lurking on alien worlds. While real ghost planets aren't likely to harbor malevolent forces, the show nails the eerie isolation of these forgotten places. Then there's Interstellar's Miller's Planet, orbiting a black hole so closely that time slows to a crawl. 1 hour there equals 7 years elsewhere. It's a dramatic exaggeration, but rooted in real physics. Einstein's relativity predicts such time warps near massive objects. The film's visuals of endless oceans churned by tidal forces, that's not far from what scientists suspect might happen on planets gripped by extreme gravity. But not all fictional ghost planets get the science right. Star Trek's Delta Vega, a frozen world improbably close to a black hole, ignores the brutal radiation that would sterilize its surface. And Superman's Krypton, exploding in a fiery cataclysm, overlooks the fact that most dying stars either fade slowly or collapse silently. Yet even these inaccuracies serve a purpose. They stretch our imagination, asking, what if, in ways that sometimes lead to real discoveries. The iconic warp drive from Star Trek, once pure fantasy, now inspires theoretical physics papers on Alcubierre drives and spacetime bubbles. Could ghost planets follow the same path from fiction to fact? Some sci-fi tropes are closer to reality than we think. The idea of a planet surviving its star's death appears in Arthur C. Clarke's The Songs of Distant Earth, where humanity flees to a world orbiting a white dwarf. Today, we know such worlds exist. Even the concept of a rogue planet, a world without a sun, was sci-fi until astronomers found them drifting between stars. The lines blur further with dead star systems like PSRB 1257+12, home to real pulsar planets that inspired Doctor Who's Croptor, a planet orbiting a black hole held in place by the Beast. While we've found no literal demons, the discovery of planets around stellar corpses proves truth can be as strange as fiction. What's truly fascinating is how sci-fi often anticipates science. The 1950s pulp classic, The Black Sun, envisioned a planet orbiting a dark star decades before black holes were confirmed to exist. Modern shows like The Expanse depict ice-hauling missions to the outer solar system, mirroring real proposals to mine water from Europa or Enceladus. This back and forth between imagination and discovery raises a provocative question. Could today's wildest ghost planet stories, like a world sustained by dark matter or a civilization thriving in a black hole's accretion disk become tomorrow's breakthroughs. History suggests we shouldn't bet against it. The real magic of these stories isn't just their spectacle, but how they prime us to see the universe as a place of infinite possibility. When a Star Wars fan gazes at a white dwarf through a telescope, they're not just seeing a dead star, they're seeing a potential Tatooine, a hidden fortress, or a gateway to another galaxy. That shift in perspective matters. Every scientific revolution begins with someone daring to imagine the impossible. Ghost planets, whether on screen or in the void, remind us that the universe's greatest mysteries often start as figments of our imagination until science pulls them into the light. Detecting intelligent life on a ghost planet would be like searching for a candle flame in a hurricane, but that doesn't mean we shouldn't look. Technosignatures, the telltale markers of advanced civilizations, could take forms we barely recognize in such an extreme environment. Imagine a species that evolved not under sunlight, but in the dim glow of tidal energy or geothermal vents, harnessing the faint warmth of a dead star's remnant. Their technology wouldn't rely on solar panels, but might tap into magnetic fields or the subtle gravitational pulses of a neutron star. The very definition of advanced shifts when your world lacks a sun. One potential technosignature could be unnatural heat patterns. Even in the freezing depths of space, concentrated energy use leaves thermal footprints. A civilization surviving underground might vent excess heat through surface structures, detectable as infrared anomalies against the icy backdrop. Or consider artificial lighting, not the sprawling city lights we imagine on Earth, but perhaps bioluminescent farms or industrial processes emitting specific wavelengths. The European Space Agency's Ariel mission, designed to study exoplanet atmospheres, could theoretically spot such anomalies if they're powerful enough. Then there's the question of communication. A species living near a pulsar might use its regular beams as a cosmic lighthouse, encoding messages in the gaps between pulses. The rhythmic precision of neutron star emissions could serve as both clock and carrier wave, a concept sci-fi explored with stories like A Message from the Heart of the Galaxy, but one rooted in real astrophysics. Alternatively, their signals might exploit quantum entanglement for instant communication across interstellar distances, leaving no conventional electromagnetic trace for us to detect. But let's be clear, the odds are astronomically slim. Without photosynthesis, the energy available for complex life is minimal. Tidal heating or radioactive decay could sustain microbial ecosystems, but building a technological civilization requires surplus energy, something a ghost planet sorely lacks. Unless these beings mastered fusion or dark matter energy, their growth would be capped by their world's meager resources. Yet history teaches us that life thrives in places we once deemed uninhabitable. Hydrothermal vents on Earth host entire ecosystems independent of sunlight. Tardigrades survive the vacuum of space. If intelligence did arise here, its technological artifacts might be unrecognizable, perhaps vast, slow-moving machines extracting energy from quantum fluctuations, or bioengineered organisms adapted to process cosmic rays. Their greatest achievement might be survival itself, enduring where physics says nothing should. The search for such signatures forces us to confront our assumptions. Our current technosignature hunts focus on radio waves and Dyson spheres, artifacts of a sunlit civilization. A ghost planet's inhabitants would play by different rules, turning darkness into an advantage. Finding them, if they exist, won't be about looking for our reflection in the cosmos, but for something utterly alien. And that's the most thrilling possibility of all. Reaching the ghost planet with today's technology is like trying to row a canoe across the Pacific. Technically possible, but utterly impractical given the staggering distances. Even if this phantom world orbits the closest known dead star, it's likely hundreds or thousands of light-years away. Our fastest spacecraft, NASA Parker Solar Probe, zips along at over 400,000 miles per hour. At that speed, crossing just 1 light-year, the distance light travels in a year, would take roughly 6,000 years. The journey to the ghost planet could span millions of years, longer than human civilization has existed. Clearly, we'd need a radical breakthrough to make this trip feasible within a human lifetime. The first hurdle is energy. Propelling a ship to even 10% of light speed requires unimaginable amounts of fuel. Conventional rockets, which rely on chemical combustion, are laughably inadequate. They'd need more propellant than exists in the solar system. Nuclear propulsion offers a glimmer of hope. Projects like Project Orion, conceived in the 1950s, envisioned spacecraft driven by controlled nuclear explosions, potentially reaching 5% of light speed. More recent concepts like nuclear thermal or nuclear electric propulsion could slash travel times to nearby stars from millennia to centuries, but even these fall short for a ghost planet hiding in the galactic depths. That's where speculative technologies enter the picture. Take antimatter engines, the most energy-dense fuel source known. When matter and antimatter collide, they annihilate each other, converting mass entirely into energy. A single gram of antimatter could release the explosive power of 40,000 tons of TNT. In theory, an antimatter-powered ship might approach light speed, cutting the journey to decades. But producing and storing antimatter remains a nightmare. We've only created microscopic amounts at facilities like CERN, at costs exceeding $60 trillion per gram. Another wild card is light sails. Instead of carrying fuel, these ultra-thin sails harness the pressure of light itself, whether from lasers or the sun, to accelerate gradually. Breakthrough Starshot, a bold initiative backed by Stephen Hawking and Yuri Milner, aims to send gram-scale probes to Alpha Centauri using gigawatt-powered lasers. Scaling this up for a crewed mission to the ghost planet would require lasers with planetary-scale energy outputs and sails the size of continents. Even then, decelerating upon arrival poses its own engineering puzzles. The real game-changer might be bending spacetime itself. Alcubierre drive, a hypothetical concept rooted in Einstein's equations, suggests warping space to create a bubble that moves faster than light without violating relativity. The ship would ride this distortion like a surfer on a wave. The catch: it requires exotic matter with negative energy, something we've never observed. Yet recent simulations show potential workarounds using intense magnetic fields or quantum effects. If achievable, an Alcubierre drive could make interstellar hops routine, turning the ghost planet into a destination rather than a daydream. But technology isn't the only challenge. Human biology crumbles under cosmic radiation, muscle atrophy, and psychological strain on decade-long voyages. Generation ships, self-sustaining arcs where multiple generations live and die en route, present ethical quagmires. Would it be fair to condemn descendants to life as interstellar passengers? Alternatively, suspended animation or digital consciousness transfer could sidestep these issues, though both remain firmly in the realm of science fiction for now. Perhaps the most sobering realization is that the ghost planet might not even exist by the time we arrive. Stars drift, orbits decay, and cosmic collisions reshape systems over millennia. Our target could be long gone, ejected into the void or swallowed by its dead star's remnants. That uncertainty underscores the bittersweet paradox of interstellar travel. The universe doesn't wait for us. Yet the very act of striving toward such an impossible journey sparks innovations that ripple across science. from energy production to materials engineering. The ghost planet isn't just a destination, it's a catalyst pushing us to rethink what's possible. The universe has a secret language ripples in the fabric of spacetime itself, carrying whispers of cosmic cataclysms across billions of light years. When a ghost planet tugs on its dead star's remnants, or when two neutron stars spiral toward collision, they don't just move through space, they warp it, sending gravitational waves cascading outward like ripples from a stone dropped into a pond. These distortions, predicted by Einstein over a century ago, are so infinitesimally small that detecting them seemed impossible until recently. Yet today, observatories like LIGO and Virgo listen for these echoes of distant chaos, and they might just hold the key to unlocking the ghost planet's deepest secrets. Gravitational wave astronomy works like a cosmic stethoscope, picking up vibrations in spacetime itself. When massive objects accelerate, whether they're black holes merging or a ghost planet orbiting a neutron star, they create waves that stretch and compress space as they pass. The effect is unimaginably subtle. The waves from even the most violent events might distort a 400-mile-long detector by less than the width of an atomic nucleus. To catch these whispers, LIGO lasers measure the distance between mirrors with precision so extreme, they could detect a hair's width shift across the distance to the nearest star. So how would a ghost planet show up in this symphony of spacetime ripples? Unlike black hole mergers that produce sharp, crashing chirps, a planet orbiting a dead star would generate a continuous hum, a gravitational purr buried under the universe's louder crashes. The planet's mass and orbit would imprint a unique signature on these waves, allowing astronomers to calculate its distance, size, and even composition without ever seeing it. Imagine deducing the shape of a bell from the sound it makes in a thunderstorm. That's the precision required to tease out the ghost planet's signal from the cosmic noise. The real challenge lies in sensitivity. Current detectors are tuned for colossal events like black holes with 30 times the sun's mass. A planet, even a gas giant, is a featherweight by comparison. But next-generation observatories, like the space-based LISA mission launching in the 2030s, could change the game. With arms spanning millions of miles, LISA will detect lower-frequency waves, the perfect range for spotting planets in wide orbits around white dwarfs or neutron stars. It's like upgrading from a microphone that only hears screams to one that catches whispers across a crowded room. What makes this approach revolutionary is its independence from light. Traditional astronomy relies on photons, whether visible, infrared, or radio, but gravitational waves bypass dust clouds, planetary debris, and even the darkness of interstellar space. A ghost planet shrouded in the ashes of its dead star, invisible to telescopes, might still broadcast its presence through spacetime's vibrations. This could reveal worlds we've missed entirely, hidden in the graveyards of long-dead stellar systems. The implications stretch beyond mere detection. By analyzing the wave's patterns, scientists could probe the planet's interior structure. Does it have a molten core generating a magnetic field? Is its mantle layered like Earth's or homogeneous like Jupiter's? Gravitational waves might even hint at exotic materials, like quark matter or super-dense elements forged in the star's death throes. It's like using sonar to map the ocean floor, except the ocean is the fabric of reality, and the floor is a world orbiting a celestial corpse. Perhaps most thrilling is the timescale. Gravitational waves travel at light speed, but they're immune to the scattering and absorption that dims starlight over distance. A signal from a ghost planet 10,000 light-years away arrives just as crisp as one from next door. This means future detectors could map the Milky Way's underworld, the hidden population of planets circling dead stars, with unprecedented clarity. every ripple would be a breadcrumb leading to another cosmic survivor, another chapter in the story of how solar systems cheat death. We're standing at the edge of a new era in astronomy where spacetime itself becomes our telescope. The ghost planet, silent and dark to conventional instruments, might soon find its voice in the universe's gravitational chorus, and when it does, we'll be listening. The Drake equation has long been our cosmic calculator for estimating intelligent life in the Milky Way, multiplying factors like star formation rates and planetary habitability. But what if we've been missing a critical variable: worlds orbiting dead stars? Ghost planets challenge every assumption in that equation, forcing us to reconsider where and how life might cling to existence. Traditional models focus on living stars, assuming planets need sunlight for energy. Yet around white dwarfs or neutron stars, tidal heating or radioactive decay could power subterranean oceans, creating oases in the eternal night. If life can thrive in Earth's deepest caves or Antarctic ice, why not in the frozen depths of a starless world? Take the equation's fraction of planets with life term. We've always pictured Earth-like worlds in cozy orbits, but ghost planets expand the possibilities. A rogue planet with a thick hydrogen atmosphere might trap geothermal heat, while a moon orbiting a gas giant near a white dwarf could be warmed by tidal flexing. Even the lifetime of civilizations factor shifts without stellar flares or ultraviolet radiation to sterilize surfaces. A ghost planet's inhabitants might enjoy quieter, longer timelines beneath protective ice shields. The equation's variables aren't just numbers, they're doors, and ghost planets could fling them wide open. Critics argue these scenarios stretch plausibility. Energy scarcity in such systems would limit complexity, making technological civilizations improbable. But extremophiles on Earth defy expectations daily, from bacteria surviving in nuclear reactor coolant to worms thriving in methane seeps. If simple life can emerge in a ghost planet's hidden oceans, intelligence might find unconventional paths, perhaps slow, deliberate civilizations that measure progress in millennia rather than centuries, their technologies built on patience rather than haste. The real twist lies in detectability. The Drake equation assumes civilizations broadcast signals we can hear, but a ghost planet's inhabitants might communicate through neutrino pulses or gravitational waves, channels we're only beginning to monitor. Their technosignatures could be as subtle as thermal anomalies in frozen wastelands or artificial isotopes in icy crusts. Our search strategies, honed for sunlit worlds, might be blind to these whispers in the dark. This isn't just academic. It reshapes our search for cosmic neighbors. Missions like JWST and the upcoming Habitable Worlds Observatory prioritize Earth twins, but adding ghost planets to the Drake framework suggests we should also scour the graves of dead stars. After all, the universe is far older than we are. Countless civilizations may have risen and fallen before our sun even ignited. Their remnants could be out there right now, orbiting stellar cadavers, waiting for us to rethink where and how we look. The silence of the cosmos might not mean we're alone. It might mean we've been listening in the wrong places. Ghost planets are more than celestial oddities. They're time capsules from the universe's distant past. Just as archaeologists piece together ancient civilizations from shards of pottery and crumbling ruins, astronomers study these orphaned worlds to reconstruct the lives and deaths of long-vanished stars. Every detail, from a ghost planet's orbit to its chemical composition, tells a story about the system it once called home. Take a planet rich in heavy metals like gold or platinum. That's a smoking gun for a violent supernova, where the explosion forged precious elements and scattered them across space. Or consider a world with a highly tilted orbit, evidence of gravitational chaos during its star's death throes. like a cosmic fingerprint left in the aftermath of destruction. These planetary fossils also reveal how stars shape their systems. A gas giant found improbably close to a white dwarf suggests the star's expansion during its red giant phase pushed inner planets outward, reshuffling the entire system like a deck of cards. Debris disks around dead stars littered with the remnants of shattered worlds hint at the brutal forces unleashed during stellar collapse. Even the absence of certain elements can be revealing. If a ghost planet lacks lightweight materials like hydrogen, it might mean its star's final outburst blasted away volatile gases, leaving behind a rocky skeleton stripped to its core. The most astonishing insights come from comparing ghost planets across the galaxy. Systems where multiple worlds survived a star's death, like the pulsar planets of PSRB 1257+12, paint a picture of solar systems that endured apocalyptic violence intact. Others, with lone survivors drifting amid debris fields, speak to systems torn apart by gravitational turmoil. By cataloging these differences, astronomers are building a cosmic timeline, showing how stellar deaths varied across epochs and galactic neighborhoods. It's like finding layers of sediment in a canyon wall, each stratum preserving a different chapter of Earth's history, except here, the canyon is the Milky Way, and the layers are made of starlight and shadow. But ghost planets don't just recount stellar obituaries, they hint at the galaxy's formative years. Some may be refugees from the Milky Way's early days, when stars formed in dense clusters and close encounters between systems were common. A planet with an orbit tilted at a bizarre angle, or one rich in rare isotopes, could be a relic from a smaller galaxy swallowed by our own billions of years ago. Others might preserve the chemical signatures of the first generations of stars, objects so ancient they burned out before Earth even formed. These worlds are cosmic Rosetta Stones, waiting for us to decode their secrets. What makes this archaeological dig so urgent is the fleeting nature of the evidence. Over billions of years, gravitational interactions erode unstable orbits, and radiation scours away atmospheric clues. Every ghost planet we find is a snapshot of a vanishing past, a whisper from an era when the galaxy looked utterly different. By studying them now, with tools like the James Webb Space Telescope and next-generation gravity wave detectors, we're racing to read these stories before they fade into the cosmic background noise. The ghost planet isn't just a survivor, it's a witness, and it's finally ready to testify. The moment we develop the technology to reach the ghost planet, we face a dilemma as old as exploration itself. Do we have the right to interfere? This isn't just about scientific discovery, it's about confronting the moral weight of touching something that has existed undisturbed for billions of years. Picture an archaeologist standing before the unopened tomb of an ancient civilization, torch in hand. The knowledge inside could rewrite history, but the act of entering risks destroying irreplaceable context. The ghost planet presents the same choice on a cosmic scale. On one side of the debate are the compelling arguments for exploration. This world could hold answers to questions we haven't even thought to ask. Its geology might preserve isotopes from the early universe, untouched by stellar winds or radiation. The chemistry of its frozen atmosphere could reveal how organic molecules behave in extreme cold, offering clues about the origins of life. There's even the slim chance of finding microbial survivors, organisms adapted to conditions we once thought impossible. The data gathered could revolutionize our understanding of planetary resilience, stellar evolution, and the boundaries of habitability. Yet the risks are equally profound. Landing a probe could contaminate the planet with Earth microbes, forever altering its pristine environment. Even distant observations with powerful lasers or scanners might inadvertently disturb delicate equilibrium. Imagine melting a critical ice layer with a misaligned beam, triggering geological collapse. And then there's the philosophical question: does this world, having outlived its star against all odds, deserve to exist without our interference? It's a relic from an era before Earth formed, a silent witness to cosmic history. Do we have the right to etch our presence onto its surface? The debate echoes terrestrial struggles over uncontacted tribes or deep-sea ecosystems. Just as we've learned that observing isolated human communities can introduce deadly diseases, our very attention might doom the ghost planet's secrets. Some ethicists argue for a prime directive approach, studying from afar without physical contact, preserving the system as a cosmic heritage site. Others counter that knowledge benefits all humanity, and that cautious, minimally invasive exploration could balance discovery with respect. Legal frameworks add another layer. Current space treaties forbid harmful contamination of celestial bodies, but enforcement is murky. Who decides what constitutes harm? If multiple nations or corporations race to exploit the planet's resources, whether for rare minerals or as a gravitational wave research outpost, could we prevent a free-for-all? The Antarctic Treaty offers a possible model, designating the continent as a scientific preserve, but space lacks a unified governing body to uphold such agreements. Perhaps the most haunting consideration is time. The ghost planet has survived eons of cosmic chaos. If we disturb it, even with the best intentions, we might erase clues that future civilizations, human or otherwise, could have deciphered with more advanced tools. It's the paradox of exploration. The act of seeking knowledge sometimes destroys the very thing we sought to understand. This isn't just about one world. It's a test case for how we'll treat the countless other relics we'll encounter as we venture deeper into the galaxy. The choices we make now will set precedents for millennia, shaping whether we become careful stewards of the cosmos or reckless tourists in the universe's grand museum. The ghost planet doesn't need us to survive, but we might need it to teach us humility. Quantum mechanics paints a universe far stranger than our everyday experience suggests. A realm where particles exist in multiple places at once, where entanglement links objects across vast distances, and where reality itself seems to flicker like a candle in the wind. Now imagine scaling those quantum quirks up to planetary proportions. Could a ghost planet, untethered from the laws governing ordinary solar systems, exhibit behaviors that blur the line between quantum weirdness and gravitational certainty? It sounds like science fiction, but the edges of known physics might allow for precisely such a paradox. Consider quantum superposition, the phenomenon where particles like electrons occupy multiple states until observed. On Earth, this effect collapses at macroscopic scales. You never see a baseball existing in two places at once. But in the extreme gravitational fields near a dead star's remnant, particularly a black hole, quantum effects might not play by the same rules. The ghost planet's orbit could exist in a probabilistic haze, its position smeared across space until some cosmic measurement, like an interaction with interstellar gas, forces it to choose a definitive path. It's as if the planet is both here and there, tracing not a single elliptical orbit but a cloud of possibilities, each weighted by the equations of quantum gravity. Then there's entanglement, the eerie connection between particles that instantly influences one another regardless of distance. If the ghost planet formed from the debris of a dying star's quantum-entangled particles, could fragments of its core remain linked across light years? Picture this: a probe lands on the planet's surface and alters a rock spin. Simultaneously, a twin rock on the other side of the galaxy, once part of the same stellar material, mirrors that change instantaneously, defying the speed of light limit. While current physics says macroscopic objects can't maintain quantum coherence, the planet's isolation and extreme environment might provide the perfect freezer to preserve such delicate states over geologic timescales. The wildest possibility involves quantum tunneling. On tiny scales, particles occasionally teleport through impassable barriers, a proton vaulting across an atomic nucleus, for example. Scale this up, and you get the speculative idea of macroscopic tunneling, the ghost planet vanishing from one orbit and reappearing in another without traversing the space between. The odds are astronomically low, but given billions of years and the extreme warping of spacetime near a black hole, even the impossible might become improbable rather than unthinkable. After all, the universe has plenty of time to roll the quantum dice. Critics rightly point out that quantum effects typically cancel out in large objects due to decoherence, environmental noise that destroys delicate quantum states. Yet the ghost planet's environment is anything but typical. Bathed in the faint whispers of Hawking radiation near a black hole or shielded by neutron star magnetic fields trillions of times stronger than Earth's, this world might experience a unique quantum preservation effect. Some theories even suggest that dark matter, if it interacts weakly with normal matter, could act as a buffer against decoherence, allowing quantum phenomena to persist at larger scales than we've ever observed. The implications would rewrite physics. A quantum-entangled ghost planet could serve as a natural laboratory to test theories of quantum gravity, bridging Einstein's relativity with the quantum realm. Its superpositioned orbit might reveal hidden dimensions predicted by string theory, or its tunneling could hint at parallel universes, with the planet briefly slipping into a neighboring cosmos before snapping back into ours. Every strange behavior would peel back another layer of reality's deepest mysteries. Of course, this remains speculative, wildly so, but history shows that today's heresies often become tomorrow's textbooks. Black holes were once dismissed as mathematical curiosities. Now we photograph their shadows. The ghost planet, a cosmic outlier in every sense, might just be the key that unlocks physics' next revolution. Until then, it lingers at the edge of our understanding, a quantum riddle wrapped in a gravitational enigma, drifting through the dark. Black holes represent the ultimate vanishing act, a star so thoroughly erased from existence that not even light escapes its grasp. Yet against all logic, planets might still cling to these cosmic voids, orbiting the very absence that once was their sun. Imagine a world circling an event horizon, where the star it was born around has collapsed into a gravitational abyss. This isn't just a ghost planet, it's a prisoner of darkness, forever bound to the universe's most unforgiving anchor. The physics of such an orbit defy intuition. A black hole's gravity isn't fundamentally different from a star's. It's just compressed into an infinitely tiny point. At a safe distance, a planet could theoretically orbit just as it would around a normal star, albeit in perpetual night. But venture too close and the rules twist. Time slows to a crawl under extreme gravity, stretching seconds into years for distant observers. Tidal forces would pull the planet like taffy, creating friction that could heat its core to molten extremes. And if the black hole spins, it might drag spacetime itself along in a vortex called frame dragging, warping the planet's path into bizarre helical spirals. Surprisingly, these worlds might not be frozen wastelands. Tidal heating, the same force that keeps Jupiter's moon Io volcanically active, could turn a black hole's ghost planet into a furnace. The energy from constant gravitational flexing might maintain subsurface oceans or even power volcanic activity, creating geothermal oases in the eternal dark. Some models suggest such planets could develop thick atmospheres trapped by intense gravity, with pressure cooking complex chemistry on their surfaces. Life here would rely not on sunlight, but on the relentless churn of tidal energy and radioactive decay, a biosphere built from the inside out. Yet the real spectacle would be the sky. A black hole's gravitational lensing would bend light from distant stars into eerie rings like a cosmic halo. The accretion disk, if one exists, might glow with X-rays and gamma rays, casting shifting shadows across the planet's surface. And if the black hole feeds on occasional gas clouds, the resulting flares could light up the heavens with brief, violent auroras, a cruel mimicry of daybreak. The question of how such a planet survives its star's collapse remains. One theory suggests it was flung outward during the supernova, narrowly escaping annihilation while the core imploded behind it. Another proposes it formed later, coalescing from debris in the black hole's surrounding disk. There's even a fringe idea that primordial black holes, hypothetical leftovers from the Big Bang, could have captured rogue planets early in cosmic history, making these systems far older than any star-born world. Detecting these orphans pushes astronomy to its limits. Traditional methods fail when the central object emits no light, but subtle clues remain. A ghost planet's gravity might perturb the orbits of nearby stars or distort the black hole's shadow in radio telescope images. Future gravitational wave detectors could catch the ripples from a planet's passage through the extreme space-time curvature, like listening for a feather's fall in a hurricane. What makes these systems so captivating is how they stretch our understanding of habitability and time. A planet orbiting a black hole could outlive all stars in the universe, persisting into the cold, dark era trillions of years from now when galaxies have faded. It's a chilling thought, civilizations rising and falling in the black hole's glow, their history written in the warped fabric of space-time itself, long after the rest of the cosmos has gone dark. The universe's last survivors might not circle stars at all, but the graves they left behind. The Fermi paradox has haunted astronomers for decades. If the universe is so vast and ancient, where is everybody? With billions of potentially habitable planets in our galaxy alone, the silence seems deafening. But what if we've been searching in all the wrong places? Ghost planets, those elusive worlds orbiting dead stars, might hold the key to this cosmic riddle. Unlike Earth-like planets basking in the glow of living suns, these shadowy survivors exist in realms we've barely begun to explore. Their very nature, dark, distant, and difficult to detect, could make them the perfect hideouts for civilizations seeking longevity in a chaotic universe. Consider the challenges of finding life on a ghost planet. Traditional SETI efforts focus on radio signals or technosignatures from sunlit worlds, assuming civilizations need stable, energy-rich environments. But a species evolving around a white dwarf or neutron star might communicate through neutrino pulses or gravitational waves channels we're only starting to monitor. Their energy infrastructure could harness tidal forces or geothermal vents, leaving no telltale signs of Dyson spheres or atmospheric pollution. To them, our frantic radio broadcasts might seem as primitive as smoke signals in a hurricane. The paradox isn't that aliens don't exist, it's that we're listening for them in a language they abandoned eons ago. Then there's the durability factor. Stars are fickle flares, supernova, and red giant expansions can sterilize entire systems in cosmic seconds. But a civilization that migrates to a ghost planet after its star's death gains a form of immortality. White dwarfs cool over trillions of years, offering a stable gravitational anchor long after living stars burn out. A society thriving in such a system wouldn't just survive, it could outlast every sun in the galaxy, evolving into something unrecognizable to our short-lived, sunlight-dependent minds. Their timelines might be so stretched that a millennium feels like a breath, making our frantic searches for contact laughably impatient. Ghost planets also solve another piece of the paradox, the Great Filter. This unsettling idea suggests some universal hurdle prevents life from advancing to interstellar communication, whether it's self-destruction, environmental collapse, or an unseen cosmic catastrophe. But what if the filter isn't disaster, but adaptation? Intelligent life might inevitably abandon unstable stellar neighborhoods for the quiet longevity of dead stars, rendering traditional detection methods obsolete. The filter could be a transition, a societal leap toward environments we've barely considered habitable. The implications are humbling. Our assumption that advanced civilizations would colonize star-rich regions like galactic arms might be backwards. The true hubs of intelligence could lie in the graveyards of dead stars, where civilizations exist in slow-motion harmony with their frozen worlds. They might view our youthful, sun-drenched planet with the same curiosity we reserve for tadpoles in a pond, interesting, but not yet worth talking to. Perhaps the silence isn't silence at all. It's just the quiet of a universe where the wisest voices whisper in the dark, waiting for us to learn how to listen. Earth's moon is more than a companion. It's a stabilizing force that keeps our planet's tilt steady, driving the seasons and regulating tides. But in the frozen darkness around a dead star, could a ghost planet boast its own lunar entourage? The answer might reshape our understanding of how moons form and survive in the universe's most hostile environments. Exomoons, moons orbiting planets beyond our solar system, have long been theorized, but detecting them pushes technology to its limits. Around a ghost planet, the challenges multiply. Without a star's light to illuminate the system, traditional methods like transit photometry, where a moon's passage dims the host planet's reflected light, become nearly impossible. Instead, astronomers must rely on gravitational storytelling. Just as the ghost planet betrays its presence through microlensing or pulsar timing, any moons might reveal themselves through subtle tugs on their host world. Picture a dancer in a darkened room, sensed only by the way their partner sways. The origins of such moons are a cosmic puzzle. Some might be survivors, born alongside their planet in the original protoplanetary disk and enduring the star's death throes. Others could be captured later, asteroids or dwarf planets snared by the ghost planet's gravity as they drifted through the interstellar void, the most intriguing possibility. Moons forged from the wreckage of the system's apocalypse. When a star dies, its violent outbursts can shatter inner planets, creating debris rings that might coalesce into new worlds or their satellites. Imagine a moon made from the remnants of its star's funeral pyre, a celestial phoenix rising from the ashes. If they exist, these moons would face extraordinary conditions. Tidal forces from the dead star's remnant, whether a white dwarf's gravity or a neutron star's magnetic fury, could stretch and heat them beyond recognition. A moon orbiting too close might be ripped apart, its fragments forming ephemeral rings. Those farther out could develop subsurface oceans from tidal flexing, much like Jupiter's Europa, but in perpetual night. Without sunlight to drive photosynthesis, any potential life would rely on chemosynthesis around hydrothermal vents, turning rock and heat into energy in slow, glacial ecosystems. The presence of moons could also stabilize the ghost planet itself. Earth's moon prevents wild axial tilts that would trigger climate chaos without it. Our poles might wander erratically over millennia. A ghost planet with a large moon might maintain a steady rotation axis, preventing temperature swings that would otherwise freeze its atmosphere solid or boil it away. Conversely, multiple moons could introduce gravitational chaos, tugging their host into erratic orbits that eventually send it careening into the void or spiraling toward its dead star's remnants. Detecting these distant companions will require next-generation tools. The Nancy Grace Roman Space Telescope's gravitational microlensing surveys might catch the telltale wobble of a moon's influence on its host planet's lensing signal. Future gravitational wave observatories could sense the ripples from moon-planet interactions around neutron stars, and if a ghost planet's moon has an atmosphere, perhaps maintained by volcanic outgassing GWST infrared eyes might sniff out its chemical fingerprints during rare alignments. The implications stretch beyond astronomy. If moons can form and persist around planets without stars, the galaxy's real estate for potential life expands dramatically. Rogue planets ejected from their systems might carry frozen moons with subsurface oceans, drifting between stars like cosmic arcs. And if civilizations ever arise in such extreme environments, their myths would tell not of a sun god, but of a moon that brought tides to their lightless world, a solitary beacon in the eternal dark. Ghost planets challenge our definitions of what makes a system habitable. With every moon we theorize, every gravitational anomaly we trace, we're forced to reconsider how tenacious and creative the universe can be. The silence of the cosmos might not mean we're alone. It might just mean we've been staring at the wrong shadows. Solitude takes on a terrifying new dimension when scaled to planetary proportions. The ghost planet, adrift in perpetual night with only the whisper of its dead star's gravity for company, embodies a loneliness so profound it challenges our very understanding of isolation. Think of the quietest place on Earth, a deep cave perhaps, or the frozen expanse of Antarctica at midnight. Now multiply that silence by billions of years, remove any hope of dawn, and stretch it across the void between galaxies. This isn't just emptiness, it's the universe's ultimate expression of abandonment, a world that outlived its purpose yet persists in the dark. What makes this cosmic solitude so unsettling is how it mirrors humanity's deepest existential fears. For centuries, we've gazed at the stars and wondered if we're alone, but the ghost planet presents a darker question. What if we're not just alone, but forgotten? It's one thing to imagine civilizations rising and falling unseen in distant galaxies. It's another to confront a world that has literally been left behind by its own sun. The psychological weight of this scenario resonates because it inverts our primal need for connection. We're a species wired for community, yet here's an entire planet condemned to eternal separation, a cautionary tale written in gravity and ice. Philosophers have long grappled with the tension between humanity's insignificance in the cosmos and our desperate need to matter. The ghost planet crystallizes this paradox. On one hand, its existence proves the universe doesn't care stars die, planets are orphaned, and the machinery of physics grinds on without sentiment. On the other, the fact that we can observe this world, ponder its fate, and even empathize with its solitude suggests something extraordinary. Consciousness might be rare, but it gives the cosmos a way to bear witness to its own indifference. In that sense, the ghost planet isn't truly alone. We're here, watching, assigning meaning to its endless night. The symbolism becomes even richer when we consider time. A human lifetime is a flicker compared to the ghost planet's billion-year vigil. Yet in our brief existence, we've developed the tools to detect this distant mourner at its star's grave. There's a tragic poetry to that, the universe's oldest orphans finally being seen by creatures who have barely learned to look up. It forces us to confront whether loneliness requires an observer to be real. If a planet drifts in darkness with no one to imagine its solitude, does it still feel the weight of isolation? Or is it simply another rock in the void until consciousness names its despair? Perhaps the most haunting lesson lies in resilience. The ghost planet didn't choose its fate, yet it endures, not thriving, not dying, just persisting in the equilibrium between collapse and escape. In that, it becomes an unexpected mirror for the human condition. we too face existential coldness, not from dead stars but from the vast indifference of time and space. Our strategies aren't so different. We orbit memories of warmth, build shelters against the void, and sometimes, like this planet, find stability in the mere act of continuing. The ghost planet's greatest gift might be showing us that solitude isn't an ending, it's simply another way to exist, one that forces us to define meaning on our own terms. Ultimately, this lonely world holds up a black mirror to our place in the cosmos. It's a reminder that the universe will outlast us, that stars will die and planets will wander, and that all our struggles might leave no more mark than a whisper in the dark. But it also proves that to be small doesn't mean to be insignificant, because in the act of contemplating this distant, frozen exile, we've already defied the silence. The ghost planet may be alone, but in seeing it, we refuse to let the universe forget. The James Webb Space Telescope isn't just another instrument, it's a cosmic game-changer, a technological marvel designed to peer into places no telescope has reached before. And when it comes to ghost planets, worlds shrouded in the darkness of dead stellar systems, Webb's capabilities could crack open mysteries we've barely begun to imagine. Unlike traditional telescopes that rely on visible light, Webb's infrared eyes cut through cosmic dust and cold, detecting the faintest whispers of heat radiating from objects too dim or distant for other observatories. Picture trying to find a black cat in a pitch-black room with only a flashlight. Now imagine switching on thermal vision. Suddenly, the invisible becomes vivid. One of Webb's most potent tools is its ability to analyze the chemical fingerprints of planetary atmospheres, or what's left of them. When a ghost planet passes in front of a distant star, even one long dead, starlight filtering through its atmosphere, if it has one, carries clues about its composition. Webb's near-infrared spectrograph can dissect that light, revealing molecules like methane, water vapor, or even industrial pollutants. Imagine discovering a planet with an atmosphere rich in chlorofluorocarbons, chemicals linked to artificial processes. It wouldn't just hint at life, it'd scream civilization. While the odds are slim, Webb turns speculation into testable science, probing whether these frozen relics could harbor more than just geologic secrets. But the real revolution lies in Webb's capacity to study dead stars themselves. White dwarfs, the cooling embers of sun-like stars, emit faint infrared glow that Webb can capture with unprecedented clarity. Any planets orbiting them would leave subtle gravitational imprints or debris trails, hints of a system's violent past. Take the case of WD 1856+534, a white dwarf surrounded by a shattered planetary disk. Webb's infrared gaze could spot the thermal echoes of collisions between asteroids or comets, painting a vivid picture of how planets survive or perish when their star dies. Then there's the tantalizing possibility of direct imaging. While ghost planets emit no visible light, their heat signatures, especially young, still warm worlds, might glow faintly in infrared. Webb's coronagraphs, which block starlight to reveal dimmer objects nearby, could potentially capture the first ever image of a planet orbiting a white dwarf or neutron star. It'd be like photographing a firefly hovering next to a blown-out light bulb. And with targets like the pulsar system PSRB 1257+12, where planets already defy expectations, Webb might uncover entirely new classes of worlds clinging to stellar corpses. The telescope's long-term observations also open doors to dynamical studies. By monitoring ghost planet candidates over years, Webb could trace their orbits with precision, revealing whether they're stable or teetering on the edge of ejection. These measurements would test wild theories like dark matter's influence on planetary motion or the survival of moons in extreme gravity wells. Every data point adds to a growing catalog of how solar systems behave when their engines shut down. What makes Webb's mission so pivotal is timing. Many ghost planets, if they exist, are cooling relics of a bygone cosmic era. With each passing millennium, their thermal signatures fade further into the background hum of the universe. Webb offers a narrow window to catch them before they vanish into the cold forever. It's not just about finding these worlds, it's about resurrecting their stories from the brink of oblivion, one infrared photon at a time. The hunt for ghost planets isn't just scientific curiosity, it's a reckoning with the impermanence of solar systems. Webb's discoveries could show us how common it is for worlds to outlive their stars, or whether our own solar system's fate might leave Earth as just another silent wanderer in the dark. With every new observation, we're not just mapping the cosmos, we're reading our own epitaph in the stars. What if the ghost planet isn't a planet at all? Imagine an ancient civilization, billions of years ahead of us, constructing a machine so vast it rivals worlds. A megastructure designed to harness the energy of a dying star or survive the cold expanse of interstellar space. The concept isn't pure fantasy. Astronomers have long speculated about Dyson spheres, hypothetical constructs that envelop stars to capture their energy, or Matryoshka brains, nested supercomputers powered by stellar output. But a ghost planet presents an even wilder possibility, an artificial world built not around a living star, but in the aftermath of its death, repurposing the remnants of a solar system into something far stranger. The first clue might lie in the planet's composition. Natural planets form from cosmic debris, their elements following predictable ratios: silicate crusts, iron cores, and atmospheric gases shaped by geological and stellar processes. An artificial world, though, could show anomalies. Excessive metals like titanium or chromium in precise alloys might hint at structural engineering. Unusual thermal patterns, geometric heat distribution, or concentrated energy emissions could betray internal machinery. Even the absence of certain isotopes, scrubbed clean for industrial use, might leave a forensic trace. Imagine scanning a seemingly frozen world only to find its equator radiating precise, unnatural warmth like the exhaust vents of a planet-sized engine. Then there's the orbit. Natural planets follow elliptical paths shaped by gravity over eons, but a megastructure might maintain an impossibly perfect circle or a deliberately unstable trajectory to optimize energy harvesting. Consider a stellar engine, a hypothetical construct that uses a star's radiation for propulsion. If such a device outlived its star, it could coast through space on programmed momentum, its orbit a vestige of ancient navigation rather than gravitational fate. Some theorists suggest that a ghost planet's irregular wobble, dismissed as cosmic chaos, might actually be course corrections like the faint hum of a gyroscope in a vast, dormant machine. Light could also betray artificiality. While dead stars emit little visible radiation, a megastructure might leak infrared signatures from heat sinks or quantum communication arrays. The James Webb Space Telescope's infrared eyes might catch the glow of a planet radiating at a precise wavelength, not the random warmth of radioactive decay, but the orderly output of thermal management systems. Even reflected light could carry clues. Unnatural albedo patterns, like vast mirrored surfaces or light-absorbing panels, would scatter starlight differently than ice or rock. But the most compelling evidence might be what's missing. A natural planet's atmosphere erodes predictably over time, stripped by cosmic rays and stellar winds. An artificial one, however, could actively regenerate its envelope, leaving chemical fingerprints like industrial gases or isotopic ratios skewed by mass recycling. Imagine detecting chlorofluorocarbons in the atmosphere of a world 4 billion years old, a telltale sign of technology, since nature doesn't produce such compounds. Or finding the planet's surface suspiciously smooth, as if micrometeorite impacts were being repaired by unseen mechanisms. The implications stretch beyond astronomy. If a ghost planet were artificial, its builders must have mastered energy and materials on scales we can barely fathom. They might have converted their dying star's corpse into a power source, tapping the gravitational energy of a white dwarf or the spin of a neutron star. Their creation could be a refuge, a monument, or even a weapon, a cosmic doomsday device lying dormant in the dark. The chilling thought isn't just that such a thing might exist, but that we could be staring right at it, mistaking engineering for geology. Of course, extraordinary claims require extraordinary evidence. Most anomalies have natural explanations: unusual orbits from chaotic gravitational interactions, thermal oddities from tidal heating, or metallic excess from a supernova's forge. Yet the mere possibility forces us to reconsider what we label as natural. The universe is 14 billion years old. If civilizations rise and fall over cosmic time, some may have left footprints too large to recognize. The ghost planet drifting in silence could be the ultimate test of our imagination, a puzzle where the pieces fit too perfectly, whispering that sometimes nature isn't the only architect. The ghost planet drifting through the void isn't just a cosmic oddity, it's a mirror reflecting Earth's ultimate destiny. Our sun, now a steady source of warmth and light, won't shine forever. In about 5 billion years, it will exhaust its nuclear fuel, swelling into a red giant so vast it could swallow Mercury and Venus whole. Earth's fate hangs in the balance. Will our planet be reduced to ashes in the sun's final fiery embrace, or could it, like the ghost planet, outlive its star and wander the cosmos as a frozen relic? The answer lies in a delicate dance between stellar physics and celestial survival tactics. As the sun expands, its outer layers will puff away into space, shedding mass like a tree losing leaves in autumn. This loss weakens its gravitational grip, potentially allowing Earth to spiral outward to a safer orbit. But safety comes at a cost. Even if our planet escapes vaporization, the transformed sun, now a white dwarf, will emit only a faint glow, barely enough to power a child's nightlight. Earth's oceans will freeze solid, their surfaces becoming icy plains cracking under temperatures near absolute zero. The atmosphere, if it survives at all, will collapse into a thin, frozen shell, leaving the planet shrouded in perpetual twilight. This is the ghost world we might become, a silent, frozen sphere circling a dying ember in the dark. Yet survival isn't the same as habitability. The ghost planets we've discovered show that worlds can endure stellar death, but they pay a steep price. Take WD 1856 plus 534b, a gas giant orbiting so close to its white dwarf that its atmosphere is being stripped away by intense radiation. Or PSRB 1257 plus 12b, a pulsar planet bathed in deadly X-rays. These worlds exist, but they're far from hospitable. Earth, stripped of the sun's nurturing light, would face similar extremes. Without photosynthesis, ecosystems would collapse. Any remaining life would cling to geothermal vents or radioactive hotspots, retreating underground like survivors in a post-apocalyptic wasteland. The parallels between these distant survivors and Earth's future raise unsettling questions. Could humanity, or whatever we evolve into, persist in such a hostile environment? The challenges are staggering. Energy would need to be harvested from nuclear decay or tidal forces, not sunlight. Agriculture would require artificial light sources or chemosynthetic processes akin to deep-sea vent ecosystems. And the psychological toll of eternal night, with no sunrise to mark the passage of days. would test the limits of any civilization's resilience. The ghost planet's existence suggests that planets can outlast their stars, but it doesn't guarantee that their inhabitants will. There's a haunting beauty to this long-view perspective. The ghost planets we study today are cosmic time capsules, preserving snapshots of stellar systems that died billions of years before our sun even ignited. By unraveling their secrets, we're not just peering into the past, we're reading Earth's future in their icy surfaces and silent orbits. They teach us that the universe is indifferent to the fates of worlds, that stars live and die, and that survival often means adapting to conditions we'd consider unthinkable. But the most profound lesson isn't about inevitability, it's about impermanence. The ghost planet's journey reminds us that even the most stable-seeming systems are temporary. The sun's death is certain, but the story doesn't end there. Long after it fades, Earth or its remnants might still drift among the stars, a silent witness to the universe's unending transformation. And in that distant era, perhaps another civilization will gaze upon our frozen world, marveling at the echoes of a planet that once teemed with life, just as we now study the ghosts of stars long gone. The Great Filter theory looms over humanity like a cosmic shadow, the unsettling idea that some universal obstacle prevents civilizations from reaching the stars. Ghost planets, those frozen survivors orbiting long-dead stars, might hold terrifying clues to this puzzle. Picture a galaxy littered with the remnants of once thriving worlds, their civilizations snuffed out not by war or folly, but by something far more inevitable, the death of their suns. Could these silent orbs be tombstones marking the fate of countless advanced cultures, a warning written in the ruins of stellar graveyards? One interpretation of the Great Filter suggests that technological civilizations inevitably trigger their own demise, perhaps through environmental collapse, artificial intelligence gone rogue, or self-destructive wars. But ghost planets present an even darker possibility, that the universe itself conspires against longevity. No matter how advanced a society becomes, it remains tethered to the lifespan of its star. When that star dies, even the mightiest civilizations might crumble under frozen skies, their megacities buried beneath glaciers of nitrogen ice. The ruins of Earth could one day join this cosmic boneyard, our pyramids and skyscrapers preserved like insects in amber under kilometers of permafrost. Yet there's a flip side to this grim narrative. The very existence of ghost planets proves that worlds can outlast their stars, so why not their inhabitants? Some theorists argue that sufficiently advanced civilizations would see stellar death coming and adapt. Imagine species that abandon their homeworlds for interstellar arcs, or transform themselves into digital consciousnesses requiring neither warmth nor light. The absence of such survivors among ghost planets we've observed could imply something even more chilling, that intelligence, no matter how resourceful, inevitably hits a wall where survival becomes impossible. The timing of stellar death adds another layer to the mystery. Our sun will live another 5 billion years, a comfortable margin for a young species like ours. But stars smaller than the sun, called red dwarfs, can shine for trillions of years. If the galaxy is teeming with civilizations around these long-lived stars, why haven't they colonized everywhere? The silence might mean that even trillions of years aren't enough, that given enough time, all civilizations succumb to entropy, complacency, or some unseen cosmic predator. Ghost planets around white dwarfs and neutron stars could represent those who made it furthest before hitting the filter's wall. But perhaps the most unsettling thought is that we're misreading the evidence entirely. The Great Filter might not lie ahead of us in time, but behind us. Earth's complex life emerged suspiciously early in planetary terms, just 500 million years after the planet cooled. Some astrobiologists argue this lightning-fast emergence suggests life is extraordinarily rare, and we're the fluke. In this view, ghost planets are just dead rocks, their silence proof that the universe is overwhelmingly barren, and the real filter was surviving the 1,000,000,000,000 odds of evolving intelligence at all. The ghost planets lesson isn't just about doom, it's about perspective. Whether these worlds are cosmic graveyards or empty stages, they force us to confront the fragility of existence on stellar timescales. The stars that seem eternal in our skies are mortal, and with them, all they nurture. But in that mortality lies a strange hope. If civilizations can leave markers, whether ruins, art, or encoded warnings, their voices might echo long after their stars go dark. The ghost planets we study today could be someone else's message in a bottle cast across the ocean of time. The question isn't just whether we'll hit the great filter, it's whether we'll be remembered if we do. The ghost planet orbiting a star that no longer exists is more than a cosmic oddity. It's a window into the universe's deepest mysteries. This celestial survivor forces us to rethink everything we thought we knew about how solar systems live, die, and sometimes cling to existence against impossible odds. It's a testament to the universe's creativity, proving that planets can endure even when their stars vanish, that gravity's rules bend in ways we're only beginning to grasp, and that life, if it exists in such extremes, might thrive in places we once deemed uninhabitable. What makes this discovery so profound isn't just the ghost planet itself, but the questions it forces us to confront. How many other worlds are out there, silently circling the graves of their stars? Could civilizations arise in the cold, dark aftermath of stellar death? And what does it mean for our own future when the sun one day fades and Earth faces a similar fate? These aren't just academic puzzles, they're mirrors held up to our place in the cosmos, reminding us that the universe operates on timescales and scales of energy that humble even our grandest ambitions. The ghost planet also underscores how much we still have to learn. For centuries, we assumed planets couldn't exist without stars. Now, we're finding worlds that defy that logic, orbiting black holes, white dwarfs, and neutron stars, objects so strange they sound like science fiction. Each new discovery peels back another layer of cosmic mystery, showing us that the universe is far weirder, more resilient, and more inventive than we ever imagined. Who knows what other surprises are waiting in the dark just beyond the reach of our telescopes? As we wrap up this journey, remember, the ghost planet isn't the end of the story. It's an invitation to keep exploring, to stay curious, and to embrace the unknown. Every time we point our telescopes at the night sky, we're not just observing the universe, we're conversing with it, uncovering secrets written in gravity, light, and time. And if a planet can outlive its own star, what other impossibilities might be waiting for us to discover? If you've enjoyed this dive into the cosmos's shadowy corners, don't forget to like, subscribe, and share your thoughts in the comments. What's the most mind-bending space mystery you've ever heard of? Let's keep the conversation going. Until next time, keep looking up, because the universe isn't just full of stars. It's full of stories, and we've only just begun.